My dear students, we will look into BCD to binary converter in lecture 10 of module 4. So our objective is to convert BCD to binary. So what we try to do is we will look into the couple of steps such we know, which is repetitive in nature. So develop the truth table, then write the expression for output in terms of inputs, then solve them using K-maps, get the expressions from the K-map, from the expressions draw the circuit. This is the routine steps that we are following. Now we will apply the same for BCD to binary converter. Input is BCD. Okay. Output is, what is your output? Output is binary output. So now look at the input part. Input BCD code varies from BCD. In BCD what is allowed? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So here it is 0 to 9. This is 0 and this is 9. Next, equivalent binary code for the BCD code is written. Once again 0 to 9. So once the BCD is beyond 9, okay, that is not being defined. So anything beyond 9 is not there. So that is the reason why in the output anything beyond 9 is considered as don't care. So don't care represented with like this, as we have shown in the output part of binary to BCD to binary truth table, in which binary is output. So from this what we try to do, we try to try to use output in terms of output A in terms of inputs. So that we will look in and we try to convert that into that information into K-map, and then for every output there is a K-map, and we will enter those values. From that we are going to get the expressions for the outputs ABCD. Now if you look at here, these values I need to enter into the map, right? Whichever is 0, I am not bothered. So what are these values for? This is not 8 and 9. So 8 and 9 ones, right? Rest are don't cares. What are the rest all don't cares? 10, 10, 11, 10 don't care, 11 don't care, 12 don't care, 13, 14, then 15. So from this what I can do is I can combine like this, and from this what I am looking for output for A. So if you look for A, what exactly is X? So A is nothing but X. Even if you look at the table, whatever is there in the X, same thing is there. So it's valid, right? What we are doing mathematically by using K-maps, we are getting the same from the table. What is there in the table, we are converted here, of course. So let us look at further. Now you look at the B and C. So enter the values of B to get the expression for B. What are the values of B? It is 1 for these 4 cases. What are the 4? 4, 5, 6, 7. So 4, 5, 6, 7. Next, 10, 11, 12, 13. 10, 11. This is 10, 11, 12, 13. And then 14 and 15 are don't cares. Right? And what about this 4, 5, 6, 7? 4, 5, 6, 7 are ones. So can I combine like this? Yes, of course I can combine this 8. What this is going to give me is y. So this is y. Right? Where we are solving this? This we are solving for B. So here I kept the values of B, so I will get output for B. Here I am putting for C. Let's suppose C. So when 2, 3, 2, 3. So this is 2, this is 3. Then 6, 7. This is 6, 7. Of course, these are zeros. Okay. Then this is don't care, don't care, don't care, don't care, don't care, don't care. So I can combine this 4. This is for C. This I am putting it here. Okay. So what I am going to get? For this, everything is changing. So no xy will come. Here everything ZT both are changing. Here we have compared. Here we compared. This is changing. This is only Y. So Y. Here this is only Z. So it is Z. So what I got it? I got it is C as B as Y. C as Z. Okay. Earlier what I got it? A as X. Is it the truth? Let's look at B. Let's look at B. Let's change the color so that I can see the impact. See is B part is nothing but Y part is saying B and Y are equal. Compare these two. Is saying C and Z are same. Z you compare with C. It says both are same. Yes, it's both are same. Okay. Now look at the next step. Next step is D. So D, if you look at it, and T you could look at it, here are these two. Okay, here are these two. They are equal, right? Even without solving also I can say that it is D is T. So D is T. A was X. B was Y. Okay. So similarly, all A, B, C, D values for C is Z. D is T. So is there any circuit required? In step 5 we need to draw the circuit, but unfortunately there is no circuit required. Okay, what is that? You have XYZT, from there we are getting ABCD. So your X, input X is going to act as A, output A. Input Y acts as output B. Input Z acts as, okay, no circuit required, as C. Input T acts as D. So no circuit required. What is this conversion? BCD to binary. What is the reasoning? The reasoning is very simple. If you look at the table, from input to output there is no change. What is there in this table? Is same. What I mean to say is BCD equal to binary. From where to where? From 0 to 9. Hence, we don't require any particular converter for this purpose. Okay, this is what exactly the conclusion for BCD to binary converter. But whereas when you go for binary to BCD, this is not the case. Why it is not the case is, okay, in binary we can go from 0 0 0 4 zeros to 4 ones. Okay, from 0 0 to 1 0 0 1, and from BCD 0 0 0 to 1 0 0 1 they are same. But beyond 9, 10 onwards, we write 1 followed by 0, 1 followed by 1, 1 followed by 2. That's why, okay, binary to BCD we need a converter circuit, whereas for BCD to binary there is no circuitry required because they are compatible. With this, I will stop here. I hope you got it, the whole process of BCD to binary code conversion.